In this video, we're going to be discussing sketching polynomials, which is something we are often in math class asked to do. However, reaching for your graphing calculator is very easy, and I can just maybe hop over to GeoGebra, and we could be really easy to just throw it into the computer and look at the graph. But I want to know about the behavior of the solutions here. So what I'm going to do is I'm going to hook you up with some useful steps that we often use when it comes to sketching polynomials, and they happen to be written here. So let's go ahead and kind of read through these, and I would pause the video and write these down. And actually I haven't written everything, but we're going to be doing a few things like applying the leading coefficient test to determine the end behavior of the graph. Okay, we can actually tell how the polynomial must begin and end from left to right just by looking at the leading coefficient and the degree. We're also going to find a y-intercept. You notice I say just one because of course this is a function. There can only be one y-intercept. We're going to find all and any real zeros. Any complex ones we'll leave for another time. And then last but not least, we're going to test some points over test intervals. That just means we're going to plug in random x values to find some extra, x, y coordinates to kind of supplement the graph that we have. So what I want to do is, first of all, let's go ahead and consider this function that I've listed here, which is 3x to the fourth minus 4x cubed. So let's just go ahead and start with this leading coefficient test thing. We're going to sketch it by hand first. And then we're gonna go over to GeoGebra and see how well did we do. So looking at this example, leading coefficient test. Now recall leading coefficient test, we would look at the degree, okay, so both the degree and the leading coefficient here. And first thing I notice is it's even degree. So even degree would imply that it's either going to start up on the left and end up on the right, or it must have started down and ended down. And the nice thing is we have a positive leading coefficient. So what this positive leading coefficient does is it indicates that in the end our polynomial eventually heads uphill. Okay, so if it ended uphill, in this case it must have started uphill as well because we had even degree. So I'm going to go up to my graph here, this xy coordinate plane, and I'm at least going to leave myself a little note here that we know it must have started up, and then eventually on the right it's going to go up. This is a good thing. We already have an idea of what this might look like. So now something else that I didn't list up here in the steps, but we should know is this. Since it's fourth degree, it can have no more than 4 real zeros. Okay, I bring this up because a 0 is also an x-intercept, and we're going to be listing that here. But if it doesn't have 4 real zeros, the other possibilities is that it have 2 real zeros. Okay, it could have 2 or it could have 0. But it's got to be one of these possibilities here. And also this. Since it's fourth degree, or we say degree n, then we talk about turning around spots, how it can turn around, go from positive to negative slope or vice versa. But since n, our degree is 4, we could say it could turn less than or equal to 3 times. Okay, so it could either turn 3 times or it could turn around 1 time. So that being said, let's go ahead and find our y-intercept. The lovely thing about finding a y-intercept is this. Basically, a y-intercept occurs when x equals 0. So to plug in 0 for x, you find out that y would be 0. So I plug in 0. F of 0 in this case happens to be 3, 0 to the fourth, minus 4, 0 to the third, 0, 0. So instantly we know that this passes through the origin, and that's beautiful also. I'll tell you why, because we've actually gone ahead and found one of our x-intercepts. So now, if to find a y-intercept, you plug in 0 for x and solve for y. To find an x-intercept, we'll plug in 0 for y and solve for x. So what we end up with here is this. To find x-intercept, we'll say y equals 0, and we have 3x to the fourth minus 4x cubed. Okay, so now let's take a look at this. We can factor out x to the fourth here. We get 0 equals x cubed. We can factor that out. X cubed, and that's equal to 3x minus 4. So either x cubed was 0 or 3x minus 4 is 0. So let's be clear on this. What would make this statement over here true would be the fact that if we added 4 and divided by 3, we find that x is equal to 4/3. So we have, okay, 4/3 is one of our intercepts. So let's go up here and say, okay, so 1, 2, 3, 4, 5. I'm not going to draw this to scale, 10, but 4/3 would be essentially like right here. Okay, what else do we know? Well, x cubed is equal to 0. The interesting thing is, if you look at this individually, that's kind of like a third degree polynomial or power function. And what that really means is, hey, x times x equals 0, and I just have a hard time getting my students to believe this sometimes, but either x equals 0 or x equals 0 or x equals 0, you have 3 zeros here. You have to have 3 zeros here because I've got a 0 right here and 3 over here. That's our 4 real zeros. So bottom line is you have a repeated 0, and that's okay. We would just say x equals 0. And to be technically accurate, I need people to know this. We refer to x equals 0 as having a multiplicity of 3. That just means that a 0 occurred, 3 times. So we say it went through here. Okay, so what you'll see now is this, and I'll try to switch colors on us here. Why don't we go over to like a fuchsia or something like that. What we've got now is a situation where we know it started up here on the left, and it ends up here on the right, and it passes through these points. It's just, what does it do in between these x values? So what we're going to do is we're going to select from this interval, from say, way out at negative infinity up to but not including 0, because that was actually at a height of 0. And then between 0 and 4/3, we're going to test a point between here and here. And then we're going to test a point from here on out. We just want to know how this function is behaving over these x value intervals. So in terms of plugging in test values, it is the case that you probably want to choose test values that are convenient. So for example, I plug in, say, -1. So to find f of -1, just to find what this y value would be, we get 3 -1 to the 4th minus 4 -1 cubed. So essentially we turn out a 3 plus 4. When in the end, I'll let you do the order of operations there, but you get 7. So at -1, we end up with a y value of 7. 1, 2, 3, remember I wasn't going to draw us the scale. 4, 5, 6, 7. Our graph is up here. So already we know polynomials being smooth. We've got a good indication. I better put this in orange or, oh shoot, man. Well, we'll go back to this fuchsia color here for our graph. I'll just color these in. We know that it's got to go here and do some falling. It at least passes through this point. So another convenient point to choose now would be like x equals 1. Does it bounce back up, or does it pass below my x-axis between 0 and 4/3 here? So f of 1, okay, so f of 1, for the sake of simplicity, I hate to say this, f of 1, but we get 3, 1 to the 4th, minus 4, 1 to the 3rd. Essentially 3 minus 4, you get -1. So at 1, we've got a height of -1, so it passes through this point. And if you're like me, you've got a good indication that it's got to go back up again. So, it does go back up, but just to be certain how it does so, let's plug in the x value 2. The reason why is just to see what kind of a height we would be at. So we have 3, 2 to the 4th, minus 4, 2 to the 3rd. Okay, so we get 3 times 8 minus 4 times 8. Pardon me, this is not an 8. Of course, 2 to the 4th is 16. So we end up with 3 times 16 is 48. Minus 4 times 8 is 32, leaves us a difference of 16. So really not even on my graph. It just gives me a good indication that this is clear, up here at the North Pole somewhere. But basically, this sucker takes off, okay? I'm just exaggerating there. But this gives us a good sketch of this. So again, keep in mind the things we went through. We said, we found the end behavior first. We determined how many possible real zeros it could have, either 4, 2, or 0. It could turn at most 3 times, but if it didn't turn 3 times, it could turn maybe possibly once. And we noticed that it does turn around only 1 time. And furthermore, we found a y-intercept and some x-intercepts and plugged in some points in between those x-intercepts. So last thing I said we were going to do is head over here to just this graphing program. And we say f of x equals 3x to the 4th minus 4x to the 3rd. We're going to graph this, and ooh, not a bad thing. We did I say a decent job. We did. Okay, so you see our x-intercepts here, 0 and 4/3. We had a y-intercept of 0. The end behavior definitely starts up, ends up. Okay, and we see that it turned around from negative slope, decreasing to increasing 1 time. Okay, which is consistent with it had to turn around at most 3 times, but possibly also once. So that's just kind of a gist how you would maybe sketch a polynomial function.